Alright, hello everyone. Today we are looking at formal groups. Whatever that may be. I guess we're going to find out, aren't we? That's the whole point of this series. So formal groups. First off, we're looking at the definition and some elementary examples. So we need to do a bit of setup as always. We're going to let R be a commutative ring with the unit and we're going to consider the formal power series ring in n variables, so x1 through xn, which we're going to write shorthand as Rx. We're going to let y be a vector essentially of n variables. This leads us to a definition. A formal group law in n variables, not v, in n variables is an n-tuple f to fi of formal power series with each fi being, of course, in the formal power series over R of our n copies of x and n variables over y, such that, well, first off, f of x and 0 is x, and f of 0 and y is y. And secondly, f of u and f of v and w is f of u and v and w. For examples, we have the additive group, fi of x and y just being treated as their sum. Secondly, we have the multiplicative group, on, I'll put a colon here just to make the notation more clear, on n being 1, so we're looking at 1 tuples, where f of x and y, so the additive group I is by dimension, of course it's going to extend to the whole space pretty trivially. F of x and y, we only have one of each, is going to be x plus y plus xy. Note this is our 1 plus x, 1 plus y, I guess I'll write it. This is the standard multiplicative group law. If you think about it, normally we have like 1 plus some element plus 1 plus y element. Our elements of a group are going to look like 1 plus some element. And in which case our multiplication is going to be written with our standard FOIL, 1 plus x plus y plus xy, with the 1 hidden. In case 3, we have a special case of wet groups. I don't know what a wet group is, but I guess we're going to find out. With p prime and n being 2. In that case, our group law on our first component, x1, on x1, x2, y1, y2, being x1 plus y1. And our second component in our formal law on x1, x2, y1, y2 is x2 plus y2 plus 1 over p times x1 to the p plus y1 to the p minus x1 plus y1 to the p. Now, we give elementary properties of such formal groups. Okay, so first off, each F1 has the form notation here got messed up, but I'll translate F1 of x and y Oh, I think I know. I see. I think this is supposed to be Fi up there. I gotta translate these in real time. There's a lot of typos all of a sudden. Fi being xi plus yi plus some products over alpha being at least 1, having absolute value at least 1, beta having absolute value at least 1, of c have some coefficient times x to the alpha times y to the beta. And this is directly from our first axiom, where feeding in 0 has to give the other, on one side has to give the other side. So 0 has to be a two-sided identity for each Fi. Secondly, there exists a unique phi to the x decomposing into list of phi I x with each phi I of x being a power series, formal power series on x, and phi of 0 being 0, I guess, such that phi of 0 is 0, man. So essentially no constant terms in any of the power series, and that f of x and phi of x is 0. So essentially we have an inverse for every element x, two-sided. And we note here having a unique phi x as above is a consequence of d squared, f0 being the identity on r to the n. Okay. Yeah, so I got to decode here what exactly is writing. I think this is meeting the left equation. That is like fx and phi x equals 0. And so is such a cx meeting the conditions and the right equation. Then c of x is by definition going to be equal to f of c of x and 0. Since of our first law, 0 and anything in 0 has to return it on either side. But we can then substitute this with our left-hand equation, giving 0 to be f of x and phi of x. We can then switch over our bracket by the associativity of f, which is our second condition. And now, of course, this term on the left is going to disappear, giving us f of 0 and phi of x. This is really just our standard proof that left and right hand identities have to match up on a group, except with all this weird notation now. So essentially, one of these is the left hand inverse, the other is the right hand, and the way you prove it anyways, you can show that this is the left and right hand inverses have to match up. Now, as always, there is the ever-present question of who cares. So, let's look at some important use cases. First off, we have r being equal to k, where k is a complete field. And secondly, we have r being a, which is going to be the evaluation ring of a complete ultrametric field. Okay. Oh, okay, and we're getting into category theory all of a sudden. I'm not gonna go over any category theory. Just like pretend you understand here. So, in case 1, we shall define a natural functor T from analytic groups, which are Lie groups to Lie algebras. This is very important, as you can imagine. And we will, of course, want a functor S going in the opposite direction such that T of S is identity. So essentially you have a function mapping a object in the category of Lie algebras to a Lie group, and then you can push it back and recover your Lie algebra. Is the idea here. We note that in characteristic 0, there is a category equivalence between Lie algebras and formal groups. We are going to also then use case 2 to study analytic groups, which I'm going to go ahead and write as Lie groups over a complete ultrametric field K. With a commutative diagram of functors. So we have formal groups over A, formal groups over K, and we have Lie groups over K. We have, of course, a map from Lie groups to formal groups over K, and we have a map from over A to over K in either case. And this will give us every Lie group is locally a formal group modded with its evaluation ring modded out. Alright, nothing like but a category theory to start us off. But next up, let's look at formulae. And we'll see how long this one goes, I guess. We might have to cut this chapter off halfway through, as you do. formulae. And of course we are going to write O dO over N to represent a formal power series whose homogeneous parts vanish in degree strictly less than n. We let f of x, comma y denote a formal group law over a ring R, except of course when stated otherwise. So let's look at some formulas now. First off, f of x plus y must be equal to, we know we have to have x plus y, and then we're going to write a bilinear form over x and y, which is going to be our second order terms, and then our higher order terms we're going to right away as, of course, dO cubed at least 3. With b, of course, being a bilinear form. This is our basis expression we saw before for a formal group law, since our coefficients C alpha beta vanish unless alpha and beta are at least 1. And we're going to set our bracket in this case to be, we make a bracket out of the bilinear form the way you always make a bracket out of bilinear forms. Secondly, we're going to let phi of x be the formal inverse corresponding to f. Then the inverse of x has to be negative x plus the bilinear form of x itself plus some higher order stuff. And to see this, we can write phi of x will be phi 2 of x plus higher order terms with, of course, phi I of x being homogeneous of degree I. Then got some more equations to write on a new line. New page. 0 is going to be, by definition, is f of x with its inverse phi of x which we can plug into the equation to get x plus the order 1 term of phi of x plus some higher order stuff thus our phi 1 of x has to be negative x to cancel that out. So if we retrace our steps here, we get 0 is f of x and phi of x, which we can rewrite to be x plus negative x plus phi 2 of x plus some higher order stuff plus the bilinear form of x and negative x plus some higher order stuff, and so on for higher order stuff, which gives us phi 2 of x minus b of x and x plus some higher order stuff. As before, these are only 2 terms of this homogeneous degree, so they have to cancel out. So phi 2 of x must be equal to b of x and x. Alright. Thirdly, also one quick note, I'm guessing this is going to, this phi equals phi 2, this might be phi 1, maybe I'm just missing something there, but anyways. Third equation, the conjugate of y by x can be written as y plus our bracket of x and y plus higher order stuff and we see x times y times x inverse is x plus y plus bilinear form plus more stuff plus negative x plus this is supposed to be y plus b of x and x plus higher order stuff plus b of x plus y plus higher order stuff with negative x plus higher order stuff, and then even more higher order stuff. Everything's just too high of an order, and so this gives us y plus x and y. If you cancel everything out, you get the y plus the bracket of x and y plus o of plus just higher order stuff. And in this case, because the commutator is, handy to have on hand, we are going to set x, y, x inverse. We're going to write it as y plus the bracket of x and y, and then we're going to write out all our higher order terms as being some coefficient d of alpha comma beta times x to the alpha times y to the beta. With alpha having to have size at least 1, beta having to have size at least 1, and combined having to have size at least 3. And similarly, we can get some more formulas. The proof is just that same kind of sludging through a bunch of terms. get y inverse x, y. This one you can just do it by substitution. You get x plus the bracket of x and y plus higher order terms. And we have more. I gotta shake out my hand for a minute. We have the commutator of x and y can be evaluated to be just their Lie bracket plus higher order terms. And number 6 is everybody's favorite equation here. Bracket of x and the bracket of y and z plus the bracket of y on the bracket of z and x and the bracket of z on the bracket of x and y is 0. And so we have, this is going to call on like notation probably from our first video, I think, where we have the commutator like this, and these are all our things here, y, z, and of course we can just cycle through these all. This is by P. Hall here. And we contend that x to the y, y, z is actually the bracket of x on y and z plus higher order stuff, this time of degree at least 4, with this holding also true for the other two cases by, you can substitute them in, you can look by symmetry. And we get this formula by noting that x to the y is just x plus higher order stuff of a degree at least 2. And the commutator, I believe this is, of y and z, use the bracket of y and z plus higher order stuff of at least degree at least 3. And so we can just apply our, this is all by our 5th formula. So we can just apply that again and get our result. And so we're actually done with that for this formula. And with that, we're on to our 7th formula. Because you know you can never have too many formulas here. Formulae, as you say. This is going to be, we're going to call it the mth power map. Let f0 of x be 0 and f of m plus 1 of x be our f of x on fm of x. So this is kind of mimicking our derived series. And this works for both positive and negative. M, values of m noting that f to the inverse of m is the inverse of f to the m. Then by induction, f to the m of x is just m of x plus some higher order stuff. And this generalizes to a theorem by Lazard. See that there exists unique power series C1 of x being split into components C1i, of course from 1 to n of x, through Ci of x being C, well, let's use j for our indexer here. Ci to the j x, j from 1 to n, such that, first off, C1 of some x is just x. Secondly, Ci of x is order being at least I. Thirdly, Fm of x is the sum, we can write it from I from 1 to infinity, of m choose I times Ci of x for all m in Z. Proof, I mean, because assuming these exist, they are driven directly from our Fm dx, they're obviously going to be unique, so we need existence. Suppose fx y is a system of n formal power series such that first off, f of x plus y is x plus y plus higher order terms. Secondly, we have a left identity in 0. Define f to the m for m being natural, I mean being an integer, by our familiar f0 is 0, and f to the m plus 1 is f of x and x with f to the m of x. We write f to the m of x being the sum over alpha of a alpha to the m times x to the alpha with a alpha being a map of integers into n factors of r. we're going to see that for each alpha, a to the alpha is a binomial, polynomial, function of degree of at most size of alpha to the n. That is, there are elements a alpha to the I in R to the n such that a to the alpha of m is the sum over I being at most alpha of a to the I sub alpha times m choose I. With this, we still need to prove this, but this giving the theorem by setting each ci to be the sum over alpha being at least I of a alpha to the I times x to the alpha. So how do we prove this? We show this by induction on the size of alpha. In the case that alpha is 0, this is a alpha is 0 as fm. The fm's have no constant term. Okay, the size of alpha being 1. I think this is being at least 1. And we assume, of course, this is true. True for size of beta being less than the size of alpha, strictly. We want to show that a alpha to the m is a binomial, polynomial, in m of degree at most the size of alpha. And we of course know it suffices to show that the difference between successive values of m for a alpha, which of course we can write as a alpha to the m plus 1 minus a alpha to the m, is a binomial, polynomial in m of degree being at most the size of alpha minus 1. We're going to write f of x being x plus y plus higher terms with coefficients c gamma delta times x to the gamma times y to the delta by hypothesis on f. The range is delta has to be at least 1, and the size of the sum of gamma and delta has to be at least 2. Then we can write f of m plus 1 of x to be x plus f to the m of x plus the sum of our coefficients over gamma and delta, x to the gamma, and this time we're going to substitute. This is of course x and y, not just x. But here we feed in our f of m of x to the delta. If the size of alpha is exactly 1, a alpha to the m plus 1 is a alpha to the m, and we are done. If it's greater than 1, by the comparison, we have that a alpha to the m of m plus 1 is a alpha to the m plus some s alpha to the m, with s alpha of m being the sum of the coefficients of x to the alpha in each c gamma delta, x to the gamma, f of m of x to the delta. As the size of gamma is at least 1, the only contributing terms to this S have the size of delta less than the size of alpha, on our f to the m of x delta. For such delta, the coefficients of x to the alpha minus gamma have coordinates of the sum of products product over bi indexed by our sum nu of m of coordinates of coefficients in m fm with total degree being at most I sub v. Which, being the product of binomial polynomials, is going to make it a binomial polynomial with the sum of our I sub v's being alpha minus gamma and thus less than alpha, giving that the product of our BIV has degree less than alpha. And so S has degree less than alpha, and so A alpha does, and we're done. And oh, we actually went overtime for this video a little bit. Sorry about that, but thanks for watching. Next time. Oh, you know what? We're actually right before the next chapter. We have like one line. We have a corollary. Let P be prime. Then f of P is conjugate to phi of P mod P. With fp having order of at least P mod P. Alright, and now we're done this chapter. Next up, we're looking at more formal groups, and then filtrations, and then our appendix, which I think I called something else last time. But yeah, that's our next topic. We're done for now. Thank you for watching.